Nate takes a body slam.
Last lecture. And we would like to talk about a better version of a small set of integers. And you are all supposed to have looked at the code for the second version of this, right? So, let me put up the slide and expect you to explain it to each other. So here is a small set of integers being redone. We don't expect this set to contain more than 100 items. And so we are about to create that many processes, 100 processes. Overall idea was each of these processes will hold at most one item. So it may be empty-handed, or if it is not empty-handed, it has exactly one item. Okay? And the structure of that is that. My slide is a slight simplification of the notation in order to emphasize the main ideas. And the dotted box I'm going to show you. At this point, let's observe some syntactic things. This piece of code is for the ith S process. And therefore needs to be kind of macro expanded by substituting specific values of I, ranging from 1 to 100. So for example, for S3, you would have S2 there and an S2 there. You would have an S0 there. Okay? Where is this S0 coming from? You've all read this, right? Where is the S0 coming from? No one has the answer? This is the original client. We had one server in the previous implementation of the set. We now have a group of processes. Collectively will act as a server. How many that we have in this new version of the server? 100 processes, which are shown there. And S0 is the client for all of these. It was S0 who originally raised this question about, have you got this number or not? And it is therefore S0 which should receive our answer. Okay? But on the other hand, if you look at this code as it is like now, you note that we being the, say, the third process, S3, S3 expects to receive a query from S2, right? I equals 3. Why is that? How many of you have read this? None? And I remember seeing at least a half a dozen hands raised, claiming that you have seen this in 434, 634. At the end of each term, you flush it out.
Find out whether they introduce word, what
Uh-huh.
Well, get the query also next one to find out if there was next one and so on.
These processes, these 100 processes, and it's important that you have a kind of a visual model of this. They are hooked together as in ants across the nation. First, second, third, fourth, and so on. The zeroth guy, who is not in this group, asks a question. Comes to process number 1. It may or may not answer. Or on the other hand, it may pass on this question to the next one, S number 2. So who gives the question to S number 2? S1. Only S1. Nobody else. And S number 2 may be willing to answer this. Or maybe it will pass it on to the third one, and the fourth one, and so on. And they are lined up in a pipeline like so. So each one, if I'm the IT process, I will get my questions, that is questions that I'm expected to answer, only from my preceding process. If I am I get them from I minus 1. Okay? So that's how these are labeled. Now in this case, which we are yet to see, for I equals, let's say, 3, if S2 happens to ask me, have you got this number n? I, the S3 process, thinks I know the answer. I haven't got it. I'm telling this original guy who asked this question. I'm outputting false to the original client. So we better make sure that I am the person to answer that question. If my other neighbors, either right or left neighbors, have the answer, I should not be the one to answer it. Okay? So we have the first proviso that we need to verify later on. That my predecessors did not answer this. If I am number 5, processes 1 through 4 didn't reply. Okay? And that is why I am being asked. So the thing that we have to verify later on, for now it's a hypothesis, is this. The IT process gets this question if the previous I minus 1 processes did not answer it. Okay? And therefore, in order to keep the same obligation, I will either answer it, provided I know the answer, or I will pass it on. And in the case that I'm passing on the question, then I will not answer it. Right? It will be wrong to answer it and then pass it along. Alright? So, for some reason, on this first line, the I process thinks it already knows the answer and says, no, we don't have it. On the other hand, you ask it to insert a number n. There's another query that can come along, another call that can come along on this server. It will do something that is in this dotted box. Are we clear on the setup so far? Yeah.
Is process S0 the only process allowed to initiate?
Correct. Right. Okay? Now I can add a bit more to explain why this process claims to know the answer right away on the first line. Note that the whole thing that I'm showing you so far is a loop. And all these 100 processes begin their life empty-handed. They do not have any number. While they're empty-handed, if anybody asks, have you got any number? I mean, you know you're empty-handed. No need to do any search. You just say, I don't have it. And that is the situation here. If the process is in this loop, you are known to be empty-handed. And in such a situation, if you ever get a question saying, have you got n? Answer is no. Okay? So what is happening here is, the moment you become non-empty-handed, you are going to spend the rest of your life in that dotted box. You are empty-handed and you are invisible. The moment you are asked to hold a number, you will forever get stuck from then onwards in that box. Clear? And you may wonder, well, would a process that became non-empty-handed become empty-handed ever? Well, to confuse you and to simplify my life, there's no delete operation here. So you see, we never ever delete anything. And that happens to be an exercise in the paper, which you will work on. Right? Okay, so that is the reason. Once it gets into this box, never gets out of it. Because once it holds a number, it will never ever become empty-handed. Now, having said that, the number that a process is holding may change. I may hold the number 5 right now. Later on, I may hold some other number, such as 4. Okay? And now I will explain the rest of the model, the visual model. The way we set up this line of processes is, of course, as before. And in any movement, the first so many processes are non-empty-handed. All the remaining are empty-handed. Okay? So suppose the set has, at the moment, 43 items in the set. The first 43 processes are non-empty. The remaining 47 processes are empty. Okay? Now, one more detail. The first 43, the numbers that they are holding are ordered. The first guy has the least item, second guy the next least, third one next least, and so on. Remember, this is just set. There should be no duplications. Okay? So, 43 has the highest at the moment, that being the total. And now we can look at the rest of the code. I'll make one syntactic observation and then ask you a bunch of questions. In the outer loop, we are using the variable n. In the box, we are using m as well as that n. Okay? Okay, now let's see how a typical scenario will go. Everything starts empty-handed. Our client then eventually will need to say, insert something. Otherwise, we'll never come into this box. So let's say we get the first such request. Insert some number. Imagine this number is 99. Nothing to do with the 100. 99. Okay? Now, he will send that to S1. Right? According to the convention we laid out. So if you look at this piece of code with I equals 1, what do I see here? S0, S0, right? So that's why that's the client process, the 0. Alright? So we are therefore getting S0 query insert 99. Right? And then I get into this box. I being the S1. Remember, this is the start of the set, so to speak. This is the first time we are getting one number to hold. Until now, the entire set was empty. looks like that's all I'm doing. I simply got this, get the input from S0. This n is a local variable, got bound to this 99, given by S0, and I'm now on the right hand side of this. That's all that happens. Looks okay or it looks suspicious? Looks pretty suspicious to me.
How is the process going to remember what its number is?
Well, that's the question. That's the suspicious one. Now this guy, S1, needs to remember that it now has 99. Now according to our other statements, all the remaining 99 processes are empty-handed. Because it's the first and only item in the set. So where is this item being really stored? Well, in that variable n. This n is a local variable for process number S1. And when this event is matched with the output event of S0, S0 outputted to S1, 99, using insert 99. That 99 got assigned to this n, effective, right? Right? You remember this? That something like that is equivalent to this. Okay? So that when the S1 received its first ever number, all that S1 did is to just shift gears, nothing more. It then went into this dotted box. That's all. And this is true of all processes when they receive their first ever number to hold. Until then they're empty-handed. They are in this loop. Okay? So now onwards, what happens? Well, that is, for example, imagine the question again from S0. It then asks, have you got 99? We all know the answer, yes, of course. But it goes to S1, right? So we get this query. S0 asks, has m? M equals 99. And the answer is true or not depending on this m equals n or not. And so we are answering that here. But I'm answering this only provided this number about which we received a question is less than or equal to the number that ith process is currently holding. Otherwise, I don't know the answer to this question. If this question was raised instead of 99, about 120, S1, which is holding the number 99, does not know the answer to that. It knows that it does not have it, but it cannot and must not answer no to the original question. It should send that question to the next higher process. But on the other hand, you ask this question about 93, and I am holding 99, and I receive this question. I can immediately answer it. If the number you got is equal to the number about which the question is asked, the answer is true, otherwise false. So we are outputting the value to S0 right there. Okay? On the other hand, if this has question is about m greater than the number n that I'm holding, then you ask your higher neighbor. And it is that responsibility of that higher neighbor to answer. You know this so far? And similarly, on the code, so
ask the question, do you have 93?
And I have right now 99.
Right.
And so I answer it to the original client, this Boolean result. M equals N. In this case, 93 equals 99 is the question, is the test. Answer is false. This is not assigned. Most research literature, we do not use equal sign to mean assignment. Okay. All right. Let's then look at what do I do when we get an insert request. Again, same scenario. I'm holding 99. Okay? Suppose we get the request to insert 99 again. This being a set, there should be no duplicates. So M equals 99, the number that I'm holding N equals 99, so this test succeeds. Skip is the empty statement, doesn't do anything. So we do nothing. On the other hand, suppose you ask me to insert, you ask the server to insert 105, and I'm holding 99. Well, M is 105, N is 99, so I don't need to do anything. I just ask my neighbor to do it. Now, my neighbor may be luckily empty-handed, in which case, he just changes from the outer to the inner loop. That's all he does, as before. Or on the other hand, my neighbor may be non-empty already. So we know for sure that he will have the number 100 or higher. And he will go to the same thing. Eventually we may find a neighbor who is empty-handed. What if the whole set is already full? This whole thing will crash. Okay? So as long as you are less than 100 items full, you will find an empty-handed neighbor. Okay? In that sense, this is not robustly programmed. Okay? But I'll fix that in a few minutes. So let's not worry about that. Imagine you are quite empty. So, if I'm holding 99 and you ask me to insert 105, I merely pass along the request to the next higher neighbor, and this kind of process, this kind of situation continues until we find an empty-handed neighbor. All right? Now let's imagine the following scenario. I'm still holding 99. My lower number neighbor is holding, let us say, 94. All right? I'll probably forget these numbers. So let me write 94 here, 99 with me. So we are the ith process. And the I-1 process contains 94. Now we get the request to insert 95. Okay. So we are asked to insert 95. So what does the I-1 process do? Well, this number is bigger. It can't do it. Simply asks me to do it. And now, I have 99 with me, and I'm being asked to insert 95. And remember, we have the other global invariant. These numbers should be stored in order of the processes. So I am the logical candidate to hold the 95. But I already got a number, so what do? I pass mine to the next guy, and I take on the responsibility of holding 95. So this moves on, and this goes in there. Okay? And that's what we are doing here. If M is 95, N is 99, we ask the next higher process to insert, and then the number that I'm holding in the variable named N is reassigned to the value of N, which is 95. Any questions about this? Now let us see if there are any pathological cases here. For I equals 100, what happens in this code? For I equals 100.
If we define the blue box blue, and I is 100, there is potential that we could insert request that.
Right, we are in trouble. Similarly, over here, we are referring to S101, kind of array bounds kind of error. So the natural thing to do is to have a special S101 who is a sink. If SO1 ever gets the question about have you got this, he merely says no, which is the correct answer, right? Similarly, if S101 ever gets a request to insert something, he will simply discard it and say, I've done it. Okay, and that is the way you would make this thing robust. Okay, but, as a result, you may have one of these rippling effects. When you try to insert a new number, and your set is overflowing, it is not the newest number that you lose, but the highest number that you had so far that you may lose. Okay. But if that kind of thing bothers you, well, you need to do some more programming on this. And that's why we were pretty modest and we did say a small set of integers. Okay. This is not an arbitrarily growing set of integers. Right? Now, let us observe some of the other properties. And this is a typical thing that comes up in client-server computing in a real practical sense later on. But right now, already we can discuss some of the issues. A server, if it is a good server, should be ready to do things all the time. It shouldn't keep us waiting. It should, first of all, as you know, again from real-life servers, first accept the request. If it is going to make us wait in the delivery of the request itself, we will perceive it to be bad. And of course, each request it takes a certain amount of time to do things, which is okay. So in this case, the question is, if we ask quickly, in a rapid-fire manner, insert this number, insert that number, and so on, would it keep us waiting or not?
It wouldn't keep us waiting beyond how long it would take to accept, for S1 to accept one request.
So it is possible in this network of processes that while S1 is working, S2 also is working, and S3 is also working, and so on. So in this network, at any given moment, you may find several processes actively doing things. Okay? But S0 is one client. So is it really one client in a real-life client-server situation? No. In a real-life situation, you expect a typical server to have any number of clients. But that is just this being a very primitive notation designed to talk about fundamental, intrinsic problems. We are ignoring such issues. So if you will, think of S0 as the interface for this entire server. So S0 itself receives requests from any number of clients. And S0 therefore acts to this group of processes as a receptionist. Okay? So it's not really, there's no loss of generality or power.
In this series of processes, there's really no one server. Is that true? There's a series of...
All of them together are.
They collectively they act as
Right.
a server,
Right.
because each has the ability to insert and inquire another process around it. Each one is acting as a client and a server.
Correct. But you see, this is another good quality of servers. A server, very well implemented, is usually never a single process in a real system. In a real system, each thing that appears to you, the typical client, as a single server is actually a number of processes. And when in a real life system, processes are expensive, they will at least do threads. Okay, and we'll come back to this issue when we talk about RPC related issues. But a good implementation of a so-called server usually has multiple processes inside. Okay. And you may want to replace the word processes with threads in some situations. But multiple computing agents, so to speak. Well, the next one is another fairly clever example. This is the prime number related example. Goes under the name of sieve of Eratosthenes. A very, very centuries old algorithm to produce prime numbers. And this is simply explaining the idea. And we'll show you the code in a minute. You write down all the numbers up to a limit that you are interested in. And then onwards, you cross out the non-primes. And what is left would be guaranteed prime numbers. So you start out crossing these this way. As I said, you wrote all the numbers in sequence, 2 up to whatever number you are interested in. You start from 2 and you cross out every other number, every second number. So you cross out 4, cross out 6, 8, 10, etc. And some of these numbers may get crossed out multiple times. At that point, where you started from, the very next number is guaranteed to be a prime. In this case, 3. And you start from 3 now. And you cross out every third number. And you may multiply cross the same number again. So it's obvious. So you cross out 6 again, you cross out 9, this time 9 is newly crossed out, etc. At the end of this process, the next uncrossed number is a prime, which is 5. Right? Kind of obvious thing. Crossing all the multiples. Okay? And this is what we are going to do in CSP. And so here is the setup of all the processes. We have first 100 processes that are going to look alike, given here. Okay, I'm here to show you the 3 dots. Then we have a special one-of-a-kind process, number 0, over here. Then we have one of these sync kind of processes, 101. Okay. And this is, in a certain sense, the main thing, the print. It prints out the numbers. Okay? And all of these are put together by the parallel bond. So we have altogether 100 plus 1 plus 1 plus 1 processes. There are 103 processes there. Okay? In the group. So we are implementing this sieve using 103 processes. And this is how the whole thing would work. I'm showing you the code for one of these first 100 processes. Again, we have a lined up sequence of processes. This process, being the ith one, receives one number from the preceding one. This, it implicitly trusts it to be a prime number. It doesn't question this. So the preceding, I better not give it a non-prime. Okay? So that is what is stored in P. So P here stands for prime number. And it immediately gives it to the printing process so that it can print it out on some media. And now, the job of this process, the ith process, begins. MP is a local variable in this ith process. This is initialized to this P. And then onwards, it is ready to do the following. Whatever number that it subsequently gets from the preceding process, these numbers, it doesn't immediately believe them to be primes. Remember, the first one it ever got from the I-1th process, it took it for granted that that's a prime. But then onwards, any other number it gets from the same I-1th process, this it needs to check if it is a prime or not. However, this number n has percolated through the preceding I-1 processes. Okay? And if you look through this algorithm carefully, you will understand this. The preceding I-1 processes guarantee that this n is not a multiple of any of those numbers that they have as primes. So this process, the I process here, becomes the guardian, so to speak, of the prime number P. Okay? And as numbers go past it, it follows all multiples of P. Lets out only the non-multiple of P. Okay, that is its job. It's a filter. The ith still process filters out all multiples of P. Okay. And this it does over here. So it got this n, and now it wonders, is n a multiple of P? Okay. So far, it produced 1 times P over there, MP. And this produces 2 times P, 3 times P, and so on. Okay. Until this product it is computing is related to n, like so. The given number n from the neighbor is greater than MP. So, while this is the case, the given number is greater than MP, we loop. We keep looping. The number that I have from my neighbor is greater than 5 times P. Well, then you ask, is it greater than 6 times P? Is it greater than so on and so forth? Okay. So eventually this should fail, right? Because all the numbers are finite. When we fail, what happens? Well, either n equals NP, negation of this. Right? If that is true, we'll loop one more time. So when this loop terminated, that guard was false. So we know m is less than or equal to MP. So if m equals MP, well, we have a multiple of our prime P. So we just do nothing. Do nothing meaning we do not give it to the next guy, next process. But if m is less than MP, discovered a new prime. This number n is not a multiple of any of the preceding I minus 1 primes. It is not a multiple of p itself, and therefore it must be the next prime following p. And we give it to the I minus 1 sieve. And this will be the first number. I'm sorry, we give it to the I plus first. This is the first number I plus 1 sieve gets from us. Then onwards, we'll still be passing on numbers to the sieve. Numbers that are not multiples of p. Doesn't mean that they are primes. They may be primes, they may be multiples of the next prime number. Okay? So there we are. Once again, if you think of this as a server, lots and lots of processes are active at all times. Right? When you feed a new number to the first sieve process, it is going through this loop, while other processes are going through their corresponding loops. Fair enough? Yeah.
The last statement where n is less than np, and then we send on to the next process m. You mentioned that m,
The first one that we ever gave to I plus 1 guy is guaranteed to be a prime. First one.
only the first one.
Only the first one.
Okay.
The others may or may not be. For example, say we are the process which is holding, to give a simple one, 3. Okay, we are the process which is holding p. P equals 3. Okay? In comes 4. True or false? I'm the process holding 3. And I said in comes 4. True or false? I mean, can it happen or not? Can I receive a 4? If I'm holding a 3? Why? Because 4 will be followed by the preceding process, which is in charge of prime number 2. Right? It knows that all. 4 is a multiple of 2. So kills it. So the next number we get is what? 5. Who gives me this 5? The process which is holding 2. So I get a 5. I'm holding 3. Now I wonder, is this 5 a multiple of 3? MP is immediately assigned 3. Next number we make MP is 6. Right? So we have this situation. M is 5, MP is 6. So we give it to the next guy. S3 actually. S3 will therefore get 5 from us, as is S2. Okay? Now, so that guy has the number 5 as a prime. And 4 went across, got killed by 2. 5 went across 2. We passed it to the next one, and it just grabbed and held on to it. Okay? Here comes 6. 6 gets killed by 2, prime number 2. Here comes 7. Process holding 2 says okay, passes it on to S2. This is holding 3. Now we do MP increment, and MP becomes, so far it was 6. Now it becomes 9. Right? So, M equals MP again? No. M is 7, MP is 9. So we pass this to the next process, S3. stays holding 5. It receives a 7. It then asks, well, is 7 a multiple of 5? Its own MP becomes 10. Right? And 7 is less than 10. So it gives it to the next one. S4. S4 so far is at the top. Now it gets this. And so on. Okay. So, to make this whole thing work properly, what should sieve 0 do? Yeah, go ahead.
It should send a stream of numbers with the first one being prime.
Prime. It must do that. Otherwise, whole thing will kind of get into an erroneous start because remember this P? This I being 1 minimally, it simply assumes whatever it gets the first one is a prime. It doesn't check it. So as long as 0 starts with 2, we are in good shape. Now, S0 can be kind of stupid and give 2, 3, 4, 5, etc., etc. We don't care. Beyond that. Ultimately, already knowing that even numbers need to be avoided, we could avoid even numbers. But it doesn't really matter. Okay? What should, why do I have this? Print. Let me ask it in a different way. Who are the senders to print? Is it one or many or? Print is a loop. And the 3 dots there somehow capture some method of printing the number. Let's say on the screen or whatever. But it gets, as you see, its input from the ith sieve. Is it a specific I or what? What do you think?
Could be.
All of them. So there's a multiple fan in to print. All the sieves. Excepting some. Which? What about sieve 0? What about 101? Pretty obvious. It actually, you have that statement written there. Right? So, and then you see this statement from every ith sieve. So all of these guys have a direct contact with print. So the notation in your paper explains how to do that. So this is not just the identity. This is for all I ranging from 1 to 100. 1 to 101. Not 0. And they should all be composed with tunnel bar or non-deterministic fat bar.
Yeah, the parallel bars that you've got up there, because you want sieve 0, for example, to be able to send a stream of numbers while the rest of the sieves are working. The rest of those sieves should be able to print whenever they have a prime, so they should all work in parallel.
So you believe the parallel bar in the print would work better? Do not necessarily assume that horse paper is always correct. Leave it to you. Think some more. And your answer, I'm not saying that your answer is wrong. Yeah.
You said that print will send changes from 1 to 101.
Yes.
The books, the paper.
And therefore I'm wrong and he's right? No.
I'm just
Well,
wondering.
so you wonder about it, is what I said. Move on to this one. I could be wrong, he could be wrong, all of us could be wrong. Back to this. This idea of a coroutine is unfortunately not often taught in preceding courses. So let's talk about the word coroutine itself. This word coroutine is to be compared with the generic word subroutine. Subroutine being a more generic word than function or procedure. Okay? Subroutine had a certain master-slave relation, whereas a coroutine has a peer-to-peer relation. They're equals. Okay? And that is the idea that this use of CSP is trying to capture. And let me do the following diagram. It kind of confuses most of you. But it is worth the confusion, because in the confusion is a sufficient amount of learning to do. So, A and B are routines, equal routines. And you all know how the subroutine works. What we are now wondering about is, how does a coroutine call work? Okay? So these calls that I'm showing are coroutine calls. Okay, I'm inventing a keyword, coroutine call. Suppose I call from A the coroutine call B. Okay? Imagine that this is the first such call to B. And therefore, we go to the very top of B and begin to execute within B. Okay? Eventually you run into, to make our life hard, coroutine call of A. Okay? This one being the first such is almost like a normal return. So therefore, control returns to the line that is right below this call to B. Okay? Let me. So control returns to that. And so now we are within routine A, and we execute some more, and then do a coroutine call to B. Now this is the second one. And now the difference begins to show. It will resume executing the procedure B, the routine B, where it left off before. Okay? So it doesn't go to the top of B, but it goes to the line below the previous point where things left off. Control left B at a certain point there. And now we begin to execute again some piece of code. Note that my wiggly lines are not intended to show disjoint pieces of code in actual source code. Depending on how this is written, some of this could be some of that lines of code. Okay? So eventually you will have coroutine call A. And of course, this returns to. Okay. And the reason that this is quite crucial, quite important for us is this is the simplest way to produce concurrency on a sequential machine. All single CPU systems that do concurrency ultimately do this. And viewed in that sense, process A becomes a process, B becomes a process. And we often use the word multiplex. Now, in such a system, it is not the process B that does voluntarily coroutine call A. This is forced upon it by some kind of a low-level schedule. It forces B to return. And it similarly forces A to return. Right? If these two are processes, if for some reason this got kind of sliced out, and you resume the execution of A, you resume where it left off before. And similarly, A may have used up its functions and subroutines in this notation of ours. Well, here is the simplest example of a coroutine. And the idea of subroutine should be pretty easy to see. So, let us talk about subroutines. Again, straight from the page. Having understood what a coroutine is, what should a subroutine do? Both kinds, procedure kind as well as the function kind. The caller calls upon a subroutine, and in that conceptual sense, caller waits for answers, right? Caller doesn't go along with his own work. So, compared to our old call routine B in general takes certain number of input arguments, certain number of output arguments, right? In general. And for clarity, we are grouping them in two separate lists. But they don't have to. But let's do that for a minute. So suppose our old Pascal-like procedure call looks like that. In this CSP notation, we will do that by having a process named B. To this process, we give the inputs. Okay? And then we wait for outputs. Now, how should the subroutine B look? It should be willing to accept this call from any arbitrary process. Right? So it takes these inputs and then executes body, right? Body of subroutine. Whatever you originally had. Remember, I'm trying to cook up how to do subroutines, assuming you already wrote the subroutine in the traditional way. So you give the inputs, U is X here, and this process B will then execute the body of the subroutine. And after having done the body of the subroutine, where you had either a return statement effectively in the original language, you would now say to X, you output. Right? Outputs. Right? Now, what kind of control structure should I put around B? Nothing? In general, a typical caller may call B any number of times. Unless you know that a particular subroutine is called just once. Now, by this I don't mean one occurrence of a call to B in the source code, but one execution of a call to its procedure B. Unless you know that is just one execution of a call to a B, you need something extra here. If it is just one execution, this would do. But in general, it will be multiple, so you would put brackets and a loop. Okay? Now, how would this process be terminated? Only when X terminates. So that brings us to the almost final example. And then I would like to say a few words about the term here. with a matrix. A is a 3 by 3 matrix, and you'll see what I mean by preloaded. A is preloaded into this system. This system that you see there for doing 3 by 3 computations has, as you can see, 9 processes in the middle, 3 processes on each side. Okay? And these 3 processes at any moment produce one column of the matrix IN. Okay? So, on the other hand, this eastward 3 processes are a sink. They just take the inputs and do nothing. These top 3 processes simply produce zeros whenever you need them. Okay? And the actual answers are obtained at the bottom. Okay? Now, and the code for this entire thing is written as a powerful combination of these. And the way we are identifying the processes here is with this name M with 2 indices. Okay? And the code pieces are named west, north, east, and south in the obvious way. And the middle 9 processes are center. Okay? So what is the north process doing? Remember we said it is a source of zeros. The source of zeros is simply ready and willing to produce zeros. Doesn't test anything. Keeps on outputting to I and J, 0. Note that this doesn't flood anything. Why? Because this output from north, the northmost processes, occurs only when the processes that are connected immediately below, only when these 3 are ready to take them. Okay? And the eastward processes are a sink. So they take whatever you give it and do nothing with them. Okay? So the truly interesting processes are the central ones. A typical center process, such as say 2-2, takes 2 inputs, one from immediately above, one from its right, and produces 2 outputs. One in the same row to the right, one to same column below it. Okay? And the number that it passes to the right is unchanged. Whatever it got from the left side, it gives it to the right side. But it does something to the quantity obtained from above. And within it is the number A22. Right? A is a matrix which was previously stored 1 item per these boxes. Okay? And so as you can see, it gets this number from above, and it gives, it produces this product of Aij. The center is being written for the Ij process for some value of I and some value of j. It computes this number, Aij, which is stored within the box, takes this x from above and the old sum, and it adds up all these and gives you to the one that is below. Row number increase, same column number j. see this is really a parallel algorithm in the sense that while the column of numbers are being given and while the source of zeros are being accepted, the inner processes, center processes, are all doing work. They're not idling. Okay? On the other hand, and I just want to use the word and we won't really discuss it today. On the other hand, this is really a distributed algorithm as opposed to parallel algorithm. It is distributed in the following sense. No two processes in this setup share a memory value, share a memory location. They all send, receive things that they need to receive, need to send. Each one hangs on to one preloaded value. Now, how did we preload? Well, that is a problem itself. Because after all, the matrix A needs to be stored in the center processes. And that's non-trivial. And this is, of course, just a 3 by 3 example. If you were to use this on a 100 by 100, well, the problem becomes larger. But this is where other interconnections come into play at the time of loading the matrix A. But once it is loaded, they then become this kind of connection. So this is very useful in a situation where the matrix A remains constant, but this in keeps changing. And this is surprisingly a common situation. And for that kind of setup, this algorithm is a very effective algorithm, and as you can see, it's very elegantly written. So, end of CSP lecture, and as usual, we can come back to this if there are really, really puzzling questions.